Hello students, welcome to Sarasa classes. This is Dr. Sarkar over here, and today we are going to do a broad lecture on selenium dioxide. So in this new lecture series in which I will be discussing oxidation reactions, reduction reactions, rearrangements, which I will take section by section in a chronological manner. The lecture series is obviously to help out students who are preparing for CSR and NET, GATE exams and TFR. It will also be helpful for students who are going for IIT JAM. Okay, but the focus will mostly be on the GATE and NET exam. Okay, so here we are discussing Riley's reaction in which we're going to discuss selenium dioxide as a reagent. So some physical property of selenium dioxide in which we will say that it is a white crystalline solid. Solvent in which this is soluble. In those in category A, we can see we have aromatic hydrocarbons, which includes benzene, toluene, xylene, or halobenzene. In B, we have cyclic ethers like tetrahydrofuran, which is THF or 1,4-dioxane. We can also have alcohols such as methanol or ethanol. It can also be dissolved in acetic acid or in water. So these are the range of solvents in which selenium dioxide can function as an oxidizing agent. What are the applications for this reagent? The first thing that every IIT, JEE, or say students for going for IIT JAM exams, they will study, which is oxidation of reactive methyl or methylene groups. Herein, various aldehydes and ketones having alpha-methylene group. Okay, that is the carbonyl CO group, and next to that we have a CH2 or a CH3 group. Can be converted to the corresponding 1,2-dicarbonyl compound. So selenium dioxide or Riley's reaction is mainly used to prepare 1,2-dicarbonyl compounds. Okay. So here is an example, obviously established by Riley in 1932. And we can see we have taken a ketone in which both the alkyl groups are different. Here R1 and R2 is indicating that. So there is a possibility of oxidation taking place as either this alpha carbon, that is a methylene group, or over this methylene group. Now since the R are different, so the possibility is that when C double bond is joining here, our product is this one, and when C double bond is formed here, our product is that one. So we will say for this type of asymmetrical ketones, we will get two types of regioisomeric 1,2 diketones. However, if you take an aldehyde, in warm arm you will be having the active methylene group or the CH2 group, and that will be converted to C double bond O. So here the possibility is either you will get a dialdehyde or an alpha keto aldehyde. What is the mechanism? So for oxidation of carbonyl groups, initially you need to make the enol. Then one can think a nucleophilic addition type of reaction with the selenium dioxide, which is undergoing a Pomeroy-like rearrangement wherein water is lost from it, and then subsequent workup or attack by the water, that is the O is attacking over this carbon, and after the loss of the selenious acid, okay, we are going to have the 1,2 dicarbonyl compound formed. So let's practice some examples This is a simple acetaldehyde. This is the alpha carbon, so C double bond O will be formed here. So this is our glyoxal. If we take a acetophenone, here there is a phenyl group, so there is no CH2 over here, but CH2 group is present here, and so this will be oxidized, and that should be our product. Similarly, for a symmetrical ketone like acetone, one can oxidize at this carbon or at this carbon, leading to the formation of only this product. This also is a cyclic ketone, that is cyclohexanone, and the alpha position is having CH2 group, so it will be oxidized. Some exceptional reactions are seen in cases of heterocyclic compounds where the CH3 group in the 2 position can be directly oxidized to CHO, or in cases wherein we have 1,1 diphenyl methane where the CH2 group can be directly oxidized to the keto group using selenium dioxide. Next, we can see a few more examples. Again, this alpha position is oxidized to that. For a cycloheptanone, again, the alpha position is going to be oxidized. Okay. Here too, this is the alpha position. All right. It will be oxidized selectively. For this one, this is the alpha position which is having CH2 group, so it will be oxidized over here. For this compound, that is the alpha position which will be oxidized. Okay. And again, we can see over here in another compound, this particular alpha position is getting oxidized selectively. Now let's talk about allylic hydroxylation and oxidation. Now the allylic positions in a acyclic olefin are oxidized at various different rates, and the reactivity on the depends on the substitution pattern of the substrate. Okay, so if you are given a 1,2 disubstituted alkene, then the trend of reactive will be CH, then CH2, then CH3. If you are given a geminally disubstituted alkene, the trend is CH, CH2, CH3, that is the same. If you are given a tri-substituted alkene, things get a little different over here. The oxidation takes place at the more substituted end of the double bond and over here. So first one has to decide which is the more substituted end, and the trend over here is CH to CH3, CH. These things will become clear when we take a few more examples. Now, if you are given terminal olefins, all right, it particularly yields primary allylic alcohols because there is a allylic rearrangement of the double bond undergoing over here. So, for the first example, that is A, we have given this general alkene. So over here the order or trend will be CH greater than CH2 greater than CH3. And as we can see, CH3 is not oxidized, but it is rather over here CH2 that is getting oxidized. Now for tri-substituted alkene, we said the trend is CH2, CH3, CH. So over here, this is the CH2 and that is the CH3. So this position is not oxidized, but rather it is the CH2 that is oxidized. And why we are choosing this end? Because this end is the more substituted part of the double bond. Again, when you are given a terminal alkene, it yields to the formation of what? Allylic alcohol. And there is a rearrangement. So this bond will come here at this position and the OH will be joined at this terminal CH2 group. Now, here already we can see again we have another case in which the oxidation of the acyclic olefins primarily gives rise to E-allylic alcohols. Okay, so the next point, oxidation of cyclic olefins occur in the ring and alpha to the more substituted double bond rather than the side chain. So over here we are seeing a cyclic alkene. Here N can be 1, 2, 3. That means it can be a 5-membered, 6-membered, 7-membered, or it can be also, that is a 7-membered ring. So over here the oxidation is not taking place at this terminal alkyl group, but rather it is taking place at the more substituted carbon, which is this one, and on the alpha position. Again, as we can see, for the cases of geminal dimethyl alkene, it specifically leads to the formation of allylic alcohol, and that also of the primary alcohol type. Okay, as we can see in point number 2, we have raised it, that the oxidation of acyclic olefins primarily gives rise to E-allylic alcohols, which is this one. Again, in cases of cyclic olefins where the double bond is unsubstituted, the reactivity trend is CH2 greater than CH. And at the very last point, we will say for bicyclic olefins in which none of the rings contain more than 7 carbons, the oxidation will not take place at the bridgehead position because of the Brett's rule, which says sp2 hybridized carbon is or cannot be formed at the bridgehead because of the ring strain. Few more points. Geminal dimethyl olefins exclusively give rise to E-allylic alcohols. I think this example suffices that. Or it can also form alpha beta unsaturated aldehydes. Okay. So over here, the mechanism for the allylic oxidation reaction is as shown. It is a ene type of reaction in which this hydrogen will be taken up by this oxygen and then the pi bond will be can attack over here on the selenium. Okay, and that will mean that double bond is formed here. So this is the allyl selenic acid intermediate, which further undergoes a 2,3 sigma tropic shift involving an envelope-like transition state, and that leads to the formation of alkyl selenide, which on releases undergoes removal of the selenium to form the allylic alcohol, keeping in mind that the stereochemistry has to be E over here. So whenever we have a dimethyl substituted alkene, oxidation takes place at the CH3. So this is the product. Similarly, again for this molecule, a similar thing can be said. This is a dimethyl geminal alkene. So oxidation will take place at the CH3 group. However, if it is not a dimethyl geminal alkene, then the oxidation takes place on the CH2 group, not on the CH3. Okay, that's something that we have already discussed before in the rule sections. At last, what other things can be achieved using selenium dioxide? Most importantly, dehydrogenation can be undergone at elevated temperatures. Okay, that means at high temperatures, 1,4 type of dicarbonyl compounds can be reacted with selenium dioxides to give alpha beta unsaturated ketones. We can also take ester molecules which are having 1,4 connectivity, and then also if we treat this with selenium dioxide, again it leads to the formation of a double bond. Apart from that, another one that can be thought of is, if at all selenium dioxide is used as a catalyst in presence of hydrogen peroxide, then out here trans hydroxylation of butene dioic acid leads to the formation of this product. Okay. If you check the stereochemistry of both the OH groups, they are anti to each other. Okay, so that means if you're using a cis butenoic acid, okay, or butene dioic acid I should say, then that will lead to formation of two products which are going to have enantiomeric relationship with each other. Okay, so that completes this section of oxidation reactions involving selenium dioxide. Keep visiting Source classes for other reagents and name reactions. Thank you. This is Dr. Sarkar saying goodbye. Have a great day.